Welcome, everybody. As you can see, I am not Sunny Shell. I don't think anybody could possibly be as sunny as Sunny is, but I'm here to fill in for her. Um, I'm excited about today because we have a science show for you, and I love these subjects. So I'm really looking forward to talking about this. But before we get into it, the subject is galactic clusters, galaxy clusters. But before we get into this, I want to ask you to please like and subscribe the video while we're thinking about it, because I will get into this show in subject so interested that I won't remember to do it to remind you again. So please subscribe to the channel, like this video as we go along, and check out any of our Skeptic Haven other channels. We're on YouTube, of course, primarily, but we are on Twitter now. We are active on Instagram, and you'll find a Facebook group and a Facebook page, whether or not you want private conversations or public conversations. So this is a terrific episode or terrific subject today, and we have a great guest for it, Dr. Emily Moravec. If you could introduce yourself, say hi to everybody out there who wants to learn about some science.
Yeah, hi everyone. So nice of you to join today. So my name is Emily Moravec, as Phil kindly introduced me. So I am a radio astronomer. So I got my PhD a few years ago, and I am actively studying galaxies that live in groups called galaxy clusters. And I'm really excited to talk with you all about that today.
So this is an interesting concept right off the bat. The difference between a galaxy and a galaxy cluster.
Yeah.
Can you define that for us right up front?
Yeah, happy to. So a galaxy is a simple group of it's stars and gas and dust. So there are millions of stars that are all gravitationally bound, and a very important component of almost all galaxies is a black hole at the center. So you have a black hole at the center of a galaxy with stars that are all around it. And galaxies can be a lot of different shapes, it turns out. They can be flat, like this. If you look at them, they're just as a disk. So if you look at them straight on, they're like this. But if you look at them face on, like this, they can also be a nice ball of stars around that black hole. And they can be spiral looking, actually. And then they can be just whatever random shape that they decide they want to be. So a galaxy itself is just that black hole with stars and gas that are gravitationally bound to them. And a galaxy cluster is a cluster of galaxies. And so it can be anywhere from a few tens of galaxies to a few thousands of galaxies. And how this happens is that gravity works on a much larger scale than just putting stars around a black hole. It works on this very large scale that it can actually attract individual galaxies to one another. And so you can have smaller groups of galaxies. So those can be, maybe a few tens of galaxies, to very large clusters, which can be up to a few thousand galaxies that are all orbiting around one central mass. Yeah.
I'm curious right off the bat as
Yeah.
to what I mean, certainly we know that gravity pulls things together, right? That's
Yeah.
that's how a gas field, for example, from an exploding star and more matter in that area can sort of collate together.
Yeah.
But what is it that we think causes the swarming versus having a more evenly distributed of galaxies spread across the universe?
Yeah, that's a really good question. So what it comes from is, I don't know if you've seen any of these, but you should look them up. It's really interesting. They're called cosmological simulations. So there are it's about 5 main simulations of how we think the universe has formed. including the large scale structure, such as galaxy clusters. And so what they do is they take individual particles and simulate the billions and billions of particles that are in the universe. And it starts right after the Big Bang. And they simulate what happens then to then form individual galaxies and clusters that we have today. So what they do is they simulate that and run it, and it takes hundreds of computers, so these supercomputers, to do this. And the individual clusters then form from small perturbations that happen in that initial explosion of matter from the Big Bang. You have just small differences in how just very tiny particles group together, and that ends up over millions and millions of years, that actually ends up then forming clusters of galaxies. So it forms, go ahead.
By perturbations, that's density differences?
Yes, density differences. Yes.
Okay.
Thank you for that clarification. Yes, it's density differences in the initial distribution of particles. So yeah, it's those density, it's just the small density distribution that then causes these large scale structures, which is really quite incredible. So yeah.
If you don't mind, in terms of sort of knowing what some of the definitions are, I brought some pictures, and I'm going to bring them up and see if you can explain, not see if you can explain, but definitely you can explain.
Yes.
But tell us a little bit about what the differences are here. And I'm going to start with this one, which is, let me get this is, you may know this offhand, but I don't. So this is the Hickson galaxy group, Hickson 44.
Okay.
So, and we'll go into larger and larger structures. So tell us something about this image right here.
Yeah. So one of the first things to notice about the image is you have some galaxies that you can see exactly what they are. So you have that one in the middle left-hand corner. We have this galaxy that you see this beautiful dust lane. And then you have a galaxy right to the right of it that you can see has signs of interaction. So when you see these just lanes of dust and just arms like this coming out of the galaxy, it means it's interacting with another heavenly body, usually another galaxy. So what I initially noticed about this image is you have a lot of different types of galaxies that you can actually see. And then there are a lot of just points of light. So something that's very important for astronomy and for studying galaxy clusters is it's actually the main part of finding galaxy clusters is that you have to find the galaxies that are in the cluster. And they will all be at a very similar distance from us and to one another. So where I'm going with this is that not all the galaxies you see and the points of light in this image are going to be in the group or in the cluster. But most likely, I would assume, I don't know that particular group as well, but I would assume the ones that they have, the really beautiful ones that you can see probably are all in that group. So yeah, that's one of the main things that we have to do when we study clusters is to find the cluster members or to find which galaxies in images are actually in that gravitational group.
Actually nearby.
Exactly.
I got to apologize right up front that I'm sorry. I grabbed these slides and I didn't. These are all NASA images, of course, but I didn't scale them so I wouldn't cover you. So I'm sorry that I'm
that's okay. That's fine.
when I bring them up. So that's on the smaller scale, as opposed to this is actually the Hubble Deep Field image that everybody knows, which I guess, and I jump right to it because of what you just said, that you can't tell from this image which ones are near each other, right? I mean, we know we know that this was a dark part of the sky, that when they took the image, there was a lot in there, but we don't. Is there any way for you to tell what
Mm.
would, or how would you investigate an image like that to tell if something was close enough to something else? So these are all galaxies here, except for a
Yeah.
couple of stars
Yeah. So
that
that's
would.
a really good question.
How do you
So
know what's a cluster? What's what close enough to be
yeah,
within what we call a cluster?
yeah. So you can't just look at the image. So even myself as a trained professional, I can't look at that and tell you which ones. So what we do, there are two different ways. You have to get something called the redshift of an object. So redshift is this term that describes the Doppler effect, which is when you have a car that's moving past you, when it's moving towards you, the sound is higher pitched. It gets more and more higher pitched. And so it'll be blue shifted. So, the waves are happening more frequently. They're getting pushed together. And so that's blue shifting. And then when the car starts going away, it passes you and then goes away from you. The sound gets lower pitched. And so that is when you have the wavelengths are getting stretched out more or red shifted. So when something is coming towards you, it's blue shifted. And when it's going away from you, it's red shifted. Now, space is expanding. We know that the universe is expanding. So everything you see around you is moving away from you. So it's red shifted. And what this means is that when you look at a galaxy with something called a spectrograph, that will disperse the light that you see into its colors, you can think of it this way, or into wavelengths. So we know on Earth what hydrogen, helium, nitrogen, we know what wavelength those atoms emit at specifically. And so you can look at a galaxy and then disperse the light to find different elements in that light. And you can compare where the elements actually appear to what they would be on Earth. And so you can tell then how much. So if something's far away from you, it's going to appear much further away from its rest wavelength or its Earth wavelength than if something's closer. So that's how we do that.
I was just going to
Yeah.
ask you to get more specific on that, because this is something I haven't quite understood. Yeah.
Yeah.
So let me see if I can reword this, and you tell me if I get this wrong.
Okay.
So let's think of a visible spectrum that goes from red to purple. So, and I don't know what elements have what bars, but let's just say hydrogen absorbs certain streaks of light. So you get those black lines, right, within the spectrum. So on Earth, it's going to look a certain way. So if that is shifted toward the blue or toward the red, I'm sorry, when they're going away, you said they're shifted.
They're
it's red,
shifted
right?
redder. They
It's
become
red. Okay.
redder.
So
Yeah.
if you shifted left, that's going to be toward the red, and the more it's shifted over, means it's farther away, or it's moving farther away.
Yeah. No, it's farther away.
It's farther away.
The farther away it is from where we would expect it to be on Earth. You got that exactly right. You got the concept. And maybe those watching, maybe you did a physics lab in high school or college. Was one of my favorites. Loved doing that. You would look at an element and you would see those absorption lines. So
is that can we measure that specific enough to know how far it is?
Yeah.
Or do we have to add other tests to bolster that?
Yeah, it's a good question. So yeah, you can tell pretty closely. I mean, within astronomy units, it's pretty closely. So we get it down to it's pretty precise. So it's accurate enough to tell us, what things are close together and where they are. So, but yeah, you understood the concept just right. And that's exactly it. If something's further away, you see those lines in a much redder area than you would expect on Earth. So that's how we do that. We do that. So you stick, it's called a slit. It really is just a tiny slit that you let the light through. So you stick that on every single galaxy in that image when you look at it in the sky. And then you would get the redshift for all of those different galaxies in that image. And that's how you would tell how close things are to you and to each other.
Oh, that's cool.
Yeah.
I'm also amazed at how recently this is that we've actually learned this.
Yeah. Yeah,
You
exactly.
know. Okay,
Yeah.
I'm gonna go up the ladder now. The first
Okay.
picture I showed was a cluster. No, it was a
It's a
group. It was a
I
group.
think.
It was a small amount. So now we have the cluster. This is
Mhm.
the Virgo. Yeah, the
Ah,
Virgo cluster of galaxies.
oh, yeah, that's
So
beautiful.
yeah,
Yeah.
it's a great. I clicked on the wrong thing for me. Okay, so and here's an
Oh,
overview.
good. Great.
Shows you how
Yeah.
many. So when do we go from group to cluster in terms of
Yep.
number?
That's a great question. So that is not very well defined. The main thing that defines the difference between a group and a cluster is the mass of the entire object, and that is also not even an exact cutoff. But just for general purposes, I would say if it's a few tens of objects, it's a group, and if you get over 50 and hundreds to thousands, that's a cluster. The other important
Wow.
part of a cluster is that it has something called the intercluster medium. And what that means is that it has a lot of really hot gas in it. And it's so cool because galaxy clusters are so massive as a whole, they can be, 10 to the 13 solar masses, so 10 to the 13 times the mass of our sun. They can actually attract and hold on to this gas that in between the galaxies, and it becomes very, very hot. And so I think I had shared with Wes there were some images of galaxy clusters, but if you Google galaxy clusters, you'll often see yes, like this one. Yes, yeah. So the purple is this intercluster medium or hot gas, and it's 10 to the 7 or 10 to the 8 Kelvin. It is so hot, and a galaxy cluster has that, but a galaxy group does not.
Now this is all
Yeah.
this is all right here. This is the same image measured in different ways, right?
Right. Yes, that's what I love about this one too. So you have X-ray. So as I was saying, that intercluster medium or hot gas emits at very high energies, and so we see it with X-rays because that's high energy. And then the visible light, it's from HST, the Hubble Space Telescope. You see the individual galaxies. Now, not all those galaxies we see in that image are in the cluster, as we talked about, but some of them are. And then something that I really enjoy studying is sometimes in galaxy clusters, you can have galaxies that become active. And that means that their supermassive black hole begins eating the material around it and then spitting it back out into space in the form of these jets. And that's actually my favorite thing to study is the interaction between these active galaxies and clusters.
Is that the one in the lower right that has?
Yep. So the lower right, yeah. So that central galaxy has become active, and it's shooting these really hot jets that you can see in the radio into the cluster.
Oh wow,
Yeah.
that's interesting because I was just thinking how can you tell it's shooting out
Yeah.
if a cluster is a collective of so many, but you're saying that's coming from the center,
Right.
the
Yeah.
center mass.
Yeah. So you can, well, it's coming from an individual galaxy, not the central mass, but just there are galaxies that become the most dominant galaxy in a cluster. They just become so large and so massive. And sometimes these can become active, and then their supermassive black hole shoots out these jets. And what's really interesting is that those jets then interact with the intercluster medium. So maybe on that image, you can actually see that there are bubbles, sort of. If you look close enough, you can kind of see that there are bubbles, there's less material. There's less of the purple gas around the jet than there is kind of in the middle there.
Oh, I see. On the left image, yeah, there's sort of
Yes.
a little more transparent zone
Exactly.
around that. Now,
Yeah.
what is being ejected? I mean, I know the concept of
Yeah.
Hawking radiation around a black hole, but that's not what this is it?
No, it's not. Yeah, that's a good question. So it is, it's basically just gas. It's a bunch of elements. So how a galaxy becomes active is that the black hole basically destroys something. It can be a star. If a star gets too close to the supermassive black hole, it can be destroyed. And then there's something called an accretion disk that forms next to the black hole. It's really cool. Or we don't know exactly, actually, as scientists, we don't understand completely how these galaxies become active. Another thought is that if you have two galaxies colliding, you end up just having the gas from the galaxy just gets funneled down to the black hole and you get the accretion disk. But somehow you get this accretion disk and you have this really this material that's moving very quickly around the black hole. But because the black hole is so strong and it's rotating, it creates magnetic fields. And then electrons from the accretion disk and just matter from the accretion disk get caught in those magnetic fields and they get spun out.
Oh.
So this is that's radiation that is spun out that way, and it's called synchrotron radiation.
So
that's how you get those
so
jets.
that answers the next question that came into mind was to how the direction. So an accretion disk is going to be essentially a plane.
Exactly.
Right.
Yep,
As it starts to circulate, it's going to circulate on a plane. So if you're going to get ejection, it's going to be perpendicular to that plane.
Exactly.
Is that correct?
Yep.
Okay.
That's a good question. And so that's what happens is because of those magnetic fields that then these particles and the electrons end up spiraling out, and then you get synchrotron radiation. And so that's at specific frequencies, which we can see in the radio wavelengths.
So it's not like a quasar, which has a pulse to it. It is based on when various different amounts of matter come into it. Like if a star or in this case a larger amount of mass comes in and starts to come in and gets fed off of, if you will, then it will be sending out this mass or some of this mass along the magnetic field until it consumes that amount of matter.
Yeah, right? Exactly. Yeah. And a quasar actually is a type of active galaxy. I think you're thinking pulsar. Pulsars, when you see like these periodic, or because quasars actually are a type of active galaxy as well. But yeah. They get the engine gets turned on if a star is destroyed or there's this merging system. So you've got the right idea. Yep.
I'm close.
See
the limits of my knowledge. So
yeah, you're doing great.
So when you say it has gas around it, like this here, what I'm wondering is does that imply anything? Again, we're talking about a cluster now, right? And you said that cluster is pretty broad in terms of how we define it.
Yes, it is.
It's a subjective definition, obviously, but how we define it could be many, would you say up to tens of thousands?
Yeah, usually thousands is probably the most.
Thousands. Does the amount of gas say anything about the age of that cluster? Imply anything about the age?
The amount of gas, the amount of hot gas. That's a good question. So it can actually, if I believe, I don't study the metallicity of the gas, but I know some people do, and so you can tell, even though it's hot, you can tell there can be different elements that exist in that temperature range. So I think that you can figure out the age of it, but it's not as common to do that.
I'm kind of
Yeah.
wondering what causes one cluster to have more gas than another. Is kind of
yes.
what I'm
Yeah,
getting
that's a good question. There's a few things. One, the mass of the cluster. If it is more massive, it will most likely have more gas in it because it has a larger gravitational potential well, or it has more gravity, and so it can hold on to more of that gas.
Makes sense.
Yeah. And then the other thing is it's really interesting, but you can actually have clusters that merge. So not only do you have like galaxies that merge together, over time you actually get smaller clusters that merge together to form a larger cluster. So if you have, depending on how much gas each of the two or more systems that combine together, that can determine the final amount of how much gas there is, or the state. I was thinking of the state of the merger, how close those two subsystems are into merging. So to answer your question, what determines the amount of gas? It's mainly the mass of the system, and depending on the state of if there are systems that are merging to create the cluster.
Yeah. Okay, that kind of takes me to another question. All this stuff leads to another. So I'm gonna go up the ladder one more time to superclusters.
So, yeah.
This is, if you can tell us what a supercluster is. This is called Hyperion.
Oh yeah, okay.
Galaxy. This one. Okay, start there, and then I have a slightly different follow-up.
Yeah, of course. Yeah. So this all has to do with, I love that you started with small scale and moving up to large scale, because this is also what happens. And we call this the hierarchical formation of the universe. And that just simply means you have smaller things coming together to form larger things. And that happens on all scales. As the universe evolves, as time evolves, you have more things coming together to make small things coming together to make larger things. So we have galaxies coming together to form clusters. And as I just talked about, you have clusters coming together to form larger clusters. But in the case of this Hyperion, you have clusters that are gravitationally bound to one another. And so they would eventually, over time, become one. And it's this hierarchical formation where you start with the density perturbations that we talked about in the beginning. From the Big Bang, you have those different densities that became gravitationally attracted to one another. Those formed galaxies, and then sometimes those form clusters, and it just carries on. So you have these initial differences in the density, and eventually that can actually percolate all the way down to bringing clusters together to make this giant Hyperion cluster, supercluster.
So on something like this, how many galaxies are we talking about in this scale of image?
Yeah. That are actually in that cluster. And I think what we're looking at here too is that blue is the gas that I'm talking about, that intercluster medium.
Oh, okay.
In between the different systems. So that's usually how we color code these images of clusters. So I think that's what this is. So just within the cluster, it's probably thousands, I would say, like 5 to probably more than that. I would say anywhere from like 10 to 20,000 galaxies are probably in this system, maybe more. Yeah, it's a lot of galaxies that are in that system, because I think it looks like there's at least 5 individual clusters in there, and those can each have at least 1,000.
Yeah, I was gonna say, it looks like there's like there's the left lobe, if you will, there,
Yes.
and then the center one, and then the lower
Yep.
one, and then a right one.
Yeah,
So
exactly.
those would be the clusters
Yes, I
that
think
make up a
so.
supercluster.
Yeah, exactly. So a supercluster is simply a gathering of individual clusters.
Now
So yeah,
that
it's pretty
image,
cool.
yeah, it's
Yeah.
I love the scale of this stuff. It's just amazing.
Yeah.
Um,
Yeah, it really is.
that image, when I grabbed it, it was labeled as a proto-supercluster. So what's the difference
Ah,
between a proto-supercluster and a supercluster?
yeah, it's a great question. So it's actually getting at to what I was saying. So often when we say cluster or group, it means something that has formed and it isn't currently interacting with anything else usually.
Hmm.
But so the supercluster, a supercluster itself would be just a giant cluster where you actually had 10,000 galaxies in it, and it was pretty spherical looking. But this system, you can see it has all that substructure, and you have individual clusters coming in, and so it is currently forming. So you have everything is gravitationally attracted to one another, and it's all coming together. And eventually it will look, pretty spherical-ish over millions of years. But it is called a protocluster because it's a prototype. It's in the process of becoming a giant supercluster. So does that make
Okay.
sense?
Yeah, it does. So it is. Yeah, I mean these cluster. If each one is a cluster, they're attracted. They're going to start to move together. So
Right.
eventually, just like on the not the galaxy, yeah, on the galaxy,
Yeah.
every galaxy has a black hole at the center,
Right.
right?
Exactly. Yep.
So ultimately, these black holes will merge
Yeah.
if they're close enough. So
Right.
it's the
Yep.
same thing. So
Yes.
this kind of a structure is not like it's bound together and it's going to stay in this shape. It will literally come all together
Yes.
over long time.
Exactly. Yep. It will all come together eventually. It'll just take a while, a very long while. But yes, it will all come together eventually and form one, more um, uniform blob.
That's interesting because I was wondering about that when I was coming up with questions. The influence of um, dark matter versus dark energy,
Oh, yeah,
right? So
yeah.
dark matter. Let's see if I get this right. Dark matter has gravity, right? It is
Mhm.
matter that
Yes.
does not emit light. And then dark energy is something we don't know what it is yet, but that causes the expansion of the universe.
Right.
But on the scale of certainly a solar system, expansion doesn't affect us. It takes a much larger scale. So
Exactly. Yep.
what scale I was wondering on a cluster scale, does dark energy have an effect?
Oh, yeah, that's a good question. So, um, it's like maybe on the supercluster level, but it's really dark matter. Actually, so you got those definitions perfect. And
Hmm.
so galaxy clusters do have something we talk about dark matter halos. So,
Oh,
so galaxies have them, and galaxy clusters have them as well. So we know that dark matter exists because we can see how fast stars are moving around a galaxy or in a cluster, but they're moving faster as if there's more matter than we can account for with the telescopes that we have all across the light spectrum.
moving faster within
Yeah,
the group?
within the system.
Okay.
Either so with a galaxy, it's the stars are moving faster than we would expect around in the galaxy. And then with a galaxy cluster, they're moving faster around whatever the central point of mass is. They're moving faster than we would expect from what we can see with telescopes.
Okay.
So that's dark matter. So those are in clusters, and those affect how. So these dark matter halos, or just you can think about them about as masses of dark matter, but those interact as clusters will merge and such. But so I would say that dark matter has more of an effect, and still dark energy doesn't affect the daily life, what I would call the daily life of a galaxy cluster. It still works on an even larger scale because it's kind of pushing everything away on a much larger time scale. So gravity is still, and we're at the time in the universe that gravity still can overcome dark energy, which is that force that's pushing everything, it's expanding everything away. But gravity is still working and bringing everything together. So if you have more questions about that, let me know. It's
Yeah, that's it. I mean, since you said they'll come together eventually, that it's not like the dark energy, it's not like the expansion of the universe will overcome the attraction, even on the supercluster level,
right?
Ultimately,
yes.
Which something about the relative differences of those two. I don't know if the force is the right word because we don't know exactly what it is, but okay.
No, I think so that's my understanding of what I've learned as well, is that it's dark energy works on a much even larger scale and longer time scales. So right now, as things are in time, things still do come together and gravity still reigns.
Gravity still wins. Gravity always wins.
Yeah.
We all can't fight gravity.
No, can't fight it.
Pretend it doesn't exist.
Yeah.
It's not flat. So I've got one more image that I know very little about these. So see if you can help me with this. So this is some sort of computer simulation of a supercluster, as I understand. That's about all I know about it.
Okay. That's
filaments are interesting too. So
yes, I think typically these might be magnetic.
This is called Laniakea, our home supercluster of galaxies. That's what it was labeled as.
Okay. Yeah, I actually have not seen this image, but it does look similar to many simulations that I've seen, where the background is most likely the density of either galaxies or just particles. So where you kind of see the green is probably denser areas. And I think in the middle of the image, there's a bit of red. So that's probably the densest part. Also, so either these white lines.
I think the white lines were, I've seen these before, but again, I think those are the center of density.
Okay.
And there was something about, why are there filaments? Why does it gather in filaments? And
yeah, I also could see this maybe being the
sorry.
That's okay. The path that they travel, that particles travel to get kind of along the densest points of the white lines. That
makes sense, because if that's where the mass is, that's where they're going to go.
Right. And it looked like they started out and then they all traveled. So they were attracted and then came all together sort of along these filaments. So I could see it also being, so I think that's probably what it is. It's not as common way that I see it presented, but
that's true, because you're observational. So
yeah, I was trying to, I could Google really quick, because one main one that people look at is lustrous simulation.
So what are they looking for when they do a simulation?
Oh, that's a great question. Is there a place that I could put this link?
You can do a share screen.
Or here, I could just put it in. Oh, I can't put it in the comments. Here, I'll just put it in a private chat for you, and maybe could distribute it if. Yeah. But anyway, so what? Okay, great, perfect. So what do people look like, or what do people look for when they're doing these simulations? It's really cool because you can actually do a lot of things. So you can research anything from cosmology, which is what is the universe made of? How did it begin and where is it going? To how do galaxies interact? So people will use it for all sorts of scales of things because you can look at all of that. So there are usually over 100 people on the team that are working on these. So I'm sorry, that's not a very specific answer to your question, but they look at a lot of things. Anything from about the universe and how it formed to how do galaxies interact on this large scale.
Okay.
Yeah.
I'm just like distracted now because like I want to go look at that.
Oh, right.
But
Yes. Oh, yes. I see
because
someone.
again, I love this stuff. So
Yeah.
so so let's see. I'm looking at my list of questions here that okay. How old are our clusters?
Oh,
Do we know anything about
that's a good
age?
question.
Does this does
Um,
it tell us anything about age? Whether it be a cluster or a
Sort of.
supercluster?
We don't look at that as much because it's going to sound funny, but we don't often really care about the age as much because the redshift of these objects tells you how far away it is. If something is further away from us, it is younger. It's earlier in the universe because of this,
Okay.
the finite speed of light. So light takes a finite amount of time to travel a certain distance. So if something is further away, you're seeing it as it was earlier in the universe. So let me put this into context. So the Earth, you have the Earth, you have Saturn, which is I think it's on the order of minutes, of light minutes. So it takes minutes for light to travel from Saturn to us. So you are seeing Saturn as it was minutes ago. Pluto
Okay.
is, I think it's 9 light hours. So you're seeing that light
Wow.
9 hours. You're seeing Pluto as it was 9 hours ago when you take an image of it in the sky. The next closest star is 4 light years. So you're seeing that star as it was 4 years ago. And then it keeps going. So Andromeda is the closest galaxy to us, and it's 4 billion. It's about like 4 million or billion. For astronomers, it's kind of just in the weeds there, but
Yeah.
I think it's 4 million light years away. So you're seeing it as it was 4 million years ago. So you keep doing that as we look at galaxies, and we use redshift to do that. So we kind of stack age with distance. So if you want to look at something really early in the universe, you look at something really far away. If you want to look at something that's more in the present time, you look at something that's closer. So the age of the cluster, we just kind of say how far away is it, sort of thing. Yeah.
Well, it would take I guess it would take just a certain amount of time to be a cluster, right?
Yes.
Because assuming
true.
that we
Mhm.
started with a relatively even distribution of matter, even though we have the perturbations,
Yeah.
as they start to come together, then we can define them as clusters. I guess according to we figure that out according to the redshift, then, right? Because you collect up
Yes.
all these observations, and you can take the ones that are uh, 10 billion years in
Mhm.
that range. It's kind of like it's almost like strata in archaeology, where the ones
Yeah,
in this
exactly.
zone are the ones that we know that could be uh close together, if you will, if they're nearby in the sky, kind of a thing.
Yeah, exactly. And
Interesting.
that's exactly what we do. And as we're talking about like proto-superclusters, but we also have proto-clusters. So you can imagine as you go earlier in the universe, things are less formed. And you said that as well. So you can kind of study the formation of things with that distance, because earlier in the universe, gravity hasn't had as much time to act, and so it's less formed.
pull
So
things together. That makes
yes,
sense.
exactly. So things are more massive and more formed closer to us and just closer, yeah, in general. So
That's true. More formed. That's a
yeah,
good phrase. That's a good
yeah,
phrase.
more formed.
I know I've got a couple of audience questions, but I got one more based on what you said that came to mind. When you said that dark matter halos
Yes.
are around clusters, I'm curious of the scale of a dark matter halo versus the gas halo or
Oh, the hot gas?
the hot gas.
Yeah, that's a good,
Is
it's
that
about the
is
same.
it
Yeah, it's
okay?
about the same scale. It's basically just distributed all throughout the cluster. So I would think of it as a pretty similar scale, is my understanding. I'm not a dark matter expert, but that is my understanding for observational
So
data.
it's not a halo in the sense of like
Oh,
around it,
right.
right?
Yeah.
It's all
That's
the
a good
way
point.
through it.
Yeah, it's all through it. And that's a really good point. I had never thought of that. I'm so used to calling it a halo for galaxies
It
and
just came to
clusters.
me.
Yeah, it really is just kind of, it means a spherical object usually is
Okay.
halo. I think it's because maybe halo came because some galaxies, you have, with you're looking at it, you're looking at it um, as the plane like this, and
Yeah.
the halo will extend beyond, so it's still a spherical mass even if the galaxy is just like a spiral or something, and you're looking at it this way. So I think maybe
That
that's where halo came from, but
would be the same zone even above the accretion disk that the gas would be then?
yes, it would
That the
still
gas would
be.
be a spherical
Yeah, and with a
zone of
cluster, it does extend more than the visual matter that we can see. So I think that's where halo came from, that it extends further.
hmm. Okay.
So yeah. Yeah, it's a good
Yeah.
question. I actually have to
That
ask
makes
you.
sense because I'm thinking within our solar system, we know of the Oort cloud, right?
Right.
And
Yeah.
if our solar system is it's on its own accretion disk, but then the Oort cloud is basically a sphere, but
Yeah.
it's beyond the center of it. It's further out, like what
Yeah.
twice the length of Pluto or something like that. I forget the numbers. I don't know the numbers,
Yeah.
but
Yeah.
that's more of a halo thing. So as opposed to the gas or dark matter that you've described is populating the whole area,
Yeah.
except maybe near the black holes where it just it gets kind
Yeah.
of
Yeah.
sucked in and there's not much of it there
Yeah.
because there's things to eat it up.
Yeah. So I
Okay,
think it's generally in that area, and it does extend further. So with clusters, yeah, I'm actually going to have to ask some colleagues and ask about that, about what the extent is in clusters of the halo. Yeah, that's interesting.
that's cool. All right, I'm gonna pull up a couple of questions. We got three here. This is from the
Yeah.
audience. This is from Cosmic Kyle. What
Mm.
more do we know about the Great Attractor? Could it be just the Shapley
A Shapley,
supercluster?
yeah.
Oh, Shapley? I don't know what
So
that is.
that's how I've heard it said. Yeah, I just had to quickly Google this myself, actually, because I've heard of the Great Attractor. Um, okay, so it's the idea that it's similar to the supercluster idea, that you have a point in space where you have everything seems to be attracted towards this specific point. So I'm not an expert on this. I know it's more in the area of superclusters. So unfortunately, I won't be able to provide a great answer to this, but I know there are people very interested in this. It's in the area of superclusters, and it's along this idea of that there could be. The question is, how big does this go? You have a supercluster. Is there something bigger? Is the entire universe, is there one point that everything's kind of becoming attracted to? So I think this is a really good question, and I think people are looking into it. I don't know as much about the superclusters, but yeah, it's a really interesting topic.
Okay, and I don't have any more to add to that to simplify it or not simplify it, but yeah,
That's a good
let's all
question.
Google because that's what's great about science is all the unanswered questions. There's just
Yeah, exactly.
I think of every time we find a difficult to answer question, I think there's a need for like 100 more grad students in that
Yes,
field.
exactly.
So it's like you want to know
Yeah.
where to pick those fields where there are the
Yeah.
most questions.
With the most questions, exactly.
Begin to Know asks, what is it like at the Green Bank Observatory?
Oh, it's a good question. Yeah, so that's the necklace I'm wearing is the Green Bank telescope. So life in Green Bank is very different from a normal modern life. So we have a giant single dish radio telescope. So that means we just have one giant dish. It's 110 meters wide, so about 300 feet across, and then it's 500 feet tall. And so it's a very, very sensitive instrument. Where I'm going with this is that a lot of technological devices actually interfere with the observations. So a lot of our just modern conveniences, cell phones, Bluetooth, Wi-Fi, all operate around 2 gigahertz or some such thing. And that's actually an area of scientific interest. So in Green Bank, West Virginia, there is an area that's actually 100 square miles called the radio quiet zone. So here, there's different radii, but in that area, there's also a naval station as well that takes advantage of this. There are less cell phone towers here. So if any transmitter is placed in this radio quiet zone, they have to communicate with the observatory and okay it, as we're really trying to protect specific bands of radio frequency so that we can continue to do science. So my life here is different because I have no cell phone service, I have no Wi-Fi, no Bluetooth. So that's closer to the observatory because I live on observatory property. But yeah, so we use Ethernet. So obviously I'm on the internet, but we use Ethernet cords. We don't use Bluetooth, and cell phone service usually resumes about 45 minutes away. So I have different methods of communicating with people.
So when was that built then?
I think it was, it's like the 1960,
roughly.
1960-ish actually, is when the radio quiet zone was established. But the Green Bank telescope, the main telescope that's here, was built in 2000. But it's been a quiet zone for a long time, 60s or 70s.
That makes sense. Otherwise, they wouldn't have brought it up.
Yeah.
Okay.
I will also say that the closest grocery store is 40 minutes away. So that's also different. Lots of driving.
Well, that's what 7-Elevens and some of these other small local stores are for.
Yeah.
I have another question from Cosmic Kyle. This one, it's probably not your field, so I'll give you a warning about that, but I'm going to throw it up anyways, and then feel free to say just ask somebody else on another show if that's...
Yeah.
I'm sorry. That's the same question. What is your opinion on the CCC model of cosmology? Does dark energy contradict it?
Yeah. So I just Googled this myself because I'm not as familiar with CCC cosmology. I'm familiar with more standard ones. So yeah, the one that so there.
I don't even know what that is. What is CCC?
It says it's conformal cyclic cosmology. So yeah, that's a little bit different from what I normally, because there are these standard theories of cosmology. Yeah, so my apologies, I can't quite speak to that as I'm not a cosmologist, but it's a good question.
Okay, we'll pass on that and cover that on another show. Okay, I think that pretty much goes through my questions, but I want to ask you something about when I was... Thank you, everybody.
Yeah, it's really great questions.
When I was looking at your bio, something struck me, and I'd like you to say a little something about that. You did, I forget what it was exactly, but you said that you learned a lot about how the federal government allocates money to fund research. And what can you tell us about that?
Yeah, so I took, I've had various opportunities to be involved in something called science policy. So yeah, it's a very big term and can mean a lot of different things. But to me, it just meant, how science interacts with the government. So I did two different things. There are opportunities. If you're a scientist, you can be of a part of a professional association for astronomers. It's the American Astronomical Society. And the society has once a year days where they invite and bring astronomers from all over the country, about 30. And we go and lobby the just representatives, either the Senate or the House of Representatives, and you go talk to them, your representatives from your state, and you just tell them, I'm an astronomer. This is what we're doing right now, and these are the things that we think are important. These are the bills that are coming up. Please vote this way or that way. So those are congressional visits days. So I did one of those. And then I also did a 3-month fellowship in DC during graduate school, where I worked for the National Academies of Sciences, Engineering, and Medicine. And they were created by Congress, and they are funded by Congress in that, partly by Congress, in that they form boards of scientists, and there are about 50 boards, and they advise the government on various scientific topics. For example, every 10 years, astronomers get together and determine what are the most important priorities for the government to fund in the next 10 years. This is called the Decadal Survey. And so this happens every 10 years. It just came out recently earlier. It was November of last year. And it's a really long effort. There were about 600 papers from the community submitted saying, these are the topics I think are important for the next 10 years. They assemble 9 panels that have 10 people, and they meet over the course of a year to decide, what are we going to tell Congress is important for the government to fund in astronomy in the next 10 years. So what telescopes are coming up, what telescopes still need funding, and things like that. So I was involved in that process. I was helping get early career astronomers involved. So that's science policy from an astronomer's perspective, that I learned a lot about that whole process of how science and astronomers get funding from the government.
So does the funding generally not happen unless you have a lot of advocacy behind it in a particular field?
That's a good question. You have to have someone saying something. I think, you have to have some sort of established communication. Astronomy was the first just a scientific field to do this decadal survey that I'm aware of. And so that was a really good avenue to say, please fund this. So we have an organized way to do that. And I think, you also have to have a unified front, because if you have a lot of different people saying, please fund this, it gets confusing. And with astronomy, it's such a big, it's a lot of money, and it's a lot of community effort. And so you can't have a bunch of people saying, we want this, because then nobody gets funded. And so to get something funded on such a large scale, you have to have this community effort. So all that to say, yes, I would say yes, that you really do need to have people speaking up to say something, or things won't get funded. But you can have individual people writing grants, but you need a lot of money for astronomy. So, yeah.
Yeah. And then that, to me, that says the more people you have in the field, too, the more influence your field is going to have.
Yes, I think that is also true. And that kind of goes along the lines, too, of then it's also more states are involved, so more representatives are involved, so more people are interested. So, yeah, I think that's very true as well.
And I will say that I think it requires, this is a good argument for having science education.
Yes.
Right, because we need voters that are interested in science and interested in funding research, because they are the ones who vote for the funders, right? The people who make the funding decisions. Because ultimately everything becomes not only a priority question, but a political question. Right.
Yeah, exactly. So
So
thanks
more.
everyone for voting.
Yeah,
And
please
just
do.
being
Please
interested
do.
in science. Yeah.
Especially at the younger age.
Yeah.
I'm going to close up here with one more question,
Okay.
and that is, what have we learned in the last couple years in
Oh,
your field?
my field. What have
What's
we learned?
new?
It's a
What
good
have we
question.
learned
What's
that's
new?
new?
What's new? Um, I think that well, what's new is that we're building better telescopes thanks to tax dollars and such, which is really amazing because we get to see more of the universe. And for galaxy clusters, that means you can find more galaxy clusters. So we can learn a lot more about how galaxies clusters form and evolve because you have higher statistics and you get to see a lot more. You get to see a lot of really cool anomalous things as well too. So I think the big thing right now is all sky surveys. So you have telescopes that are capable of just mapping the whole sky and mapping it very deeply. And as our telescopes get more sensitive, so we're seeing a lot more of the universe, which is so cool and really interesting. So we're learning a lot more about the details of how clusters and galaxies form and evolve. So that's the new thing, I think, and it's really exciting. So we have a lot of data, which is great, but yeah.
Yeah, that was
Of,
coming to mind too, because it was just like, we collect lots of data. Do we have enough people in this field, or do you think we need more?
I think it's yes and no, because actually astronomy has the problem right now that we're turning out too many PhDs for the number of permanent positions. So it's actually really hard to get a permanent position these days. So
Oh, wow.
it's typical to do 2 to 3 postdocs. So these are between they're after you graduate with your PhD and before getting a permanent position. And they're usually 2 to 3 years. So it's very common just all across the world in astronomy to do 2 to 3 of these, and you move all around the world before you get a permanent position.
Wow.
So there's a lot of data and it could support more, but countries of the world and just, universities, I love astronomy. A lot of people love astronomy, but it's still a more rare position. So we're turning out way too many for the number of positions that are available. So
That's interesting.
we've got lots of data, but the funding for permanent positions is actually not keeping up with the number of people that we have in the field.
Well, here again, then we need to increase the demand on the consumer side, on the public side, and we do that in part by shows like this and
Yes.
increasing the interest in the subjects. And I this is editorial, but I think we're all richer for knowing more about the universe that we live in, right? So
Yeah, I
I
agree.
think it's terrific.
Yeah.
This has been fun. I appreciate you coming on. I hope we covered a pretty good range here in the time that we
It's
had.
been a real pleasure. Thanks
So,
everybody for the questions and the interest. Thanks, Phil, for great questions and a great
thank you.
conversation. It's been a real pleasure to be with you all today.
This was fun. So check out Emily's website if you are of so interest. I'm going to do that. There's some of her research stuff on there looks very intriguing, and I'm curious. So thank you for joining us. We look forward to seeing you down the road on Skeptic Haven at some point. I really appreciate the work that you're doing,
Thank you.
and your own interest in the field. So that's pretty much it for today. I gotta make a quick shout out to our patrons. Oh, please, yes, thank you, Wes. Please like and subscribe. Like this particular video, subscribe to the channels, because we want to have enough audience to put out more and more of these shows. Sunny will be back. I'm pretty sure next week. I think she just had a trip this week. She couldn't make it. And let me jump to the private chat real quick. Thanks to our patrons, Cindy, Cindy, Bryce, Jena, Deborah, Sunny, and Aaron. Let's get that number up, people. So thank you for everybody. Thank you, Emily, for a terrific conversation. And we'll see everybody here next week.
Bye.